Record. Okay.
All right, floor is open. Who wants to start? All right, I guess we're done then.
For the metric prefixes, do we start like the ones that are on the study guides like giga, mega, kilo, centa, milli, micro, nano? Are those all ones that we have to know?
Yeah, if I had some obscure one other than that, I could tell you, like, hecto is 100 times, but hardly anybody ever uses like hectoliters or things like that. Yeah, so those are the kind of the big ones that are most important in science. Yeah.
Also, could you like go back over like how vectors relate to like velocity, force, and all that?
Yeah, so how vectors relate to velocity, force, acceleration. Yeah, so the deal there is that quantities like force and velocity and acceleration are what we call vector quantities. In other words, it's not enough just to say how big they are because they point somewhere, because they've got a direction. So temperature, it doesn't make any sense to say the temperature today is 59 degrees Fahrenheit and it's pointed north. What? You know, so something like temperature is what we call scalar. It's just a number. It doesn't have a direction that it's pointing in. But force and velocity and acceleration are examples of vectors where they point somewhere. Not only is a force of a certain strength, but it's in a certain direction. Same deal with velocity, same deal with acceleration. That's what it comes down to when we say that they're vectors. You have to know not only how big they are to specify them, but also which way they're pointing.
So then speed would not be a vector.
Speed is not a vector, right. Speed is the bigness, if you will, the size of the velocity vector. So a car, if you wanted to specify the speed of the car, you just say 55 miles per hour. If you want to specify the velocity, then strictly speaking, you have to say 55 miles per hour heading north, or something like that. Now, even physicists often get sloppy and they'll say the velocity of the car is 55 miles an hour without saying which direction it's headed. But if we're going to be consistent in physics, to say the velocity of the car, you got to say not only how fast it's going, what the speedometer says, you also have to give the compass heading. You have to say what direction the car is moving in. Yes?
So you have an actual question on the study guide that says if evolution is only a theory, why is it taught as a fact?
Yeah, so if evolution is only a theory, quote unquote, why is it taught as a fact? So people will often say, people who are against the theory of evolution, typically for religious reasons, they'll say, if evolution is only a theory, why do we teach it as a fact? And that comes down to this misunderstanding of what the words fact and theory mean scientifically versus what the words fact and theory mean in everyday language, right? So in everyday language, we will use the word theory to mean just like a guess, and fact to be something that you know is true. It's been proven to be true. So the example I like to use is Sherlock Holmes, and if I mix it up with Clue too, and remember what I'm talking about in terms of the Clue game, yeah, we can say, like in everyday language, you might have Sherlock Holmes say, I have a theory that the butler did it in the study with the crowbar. And then Sherlock goes and gathers evidence, and if everything points in the direction of his guess having been correct, he can say, you know what? It used to be I only had a theory that the butler did it in the study with the crowbar. Now I've proven that it's a fact that the butler did it in the study with the crowbar. But in science, that's not what fact and theory refer to. In science, a fact is something that's been observed to be true about the world, like things fall when you drop them. The sun rises and sets every day, if you're in the right range of latitudes. Things like that, things we just observed to be true about the world. And scientific theories are systematic explanations of facts. So in other words, with a theory, it's not that it's a guess, it's that it's an explanation. So the theory of evolution refers to Darwin's big insight that if you have a competition between living things trying to leave behind descendants, that if they have characteristics that make them better suited to surviving to leave behind children, on average they'll leave behind more children. So this whole idea of evolution by natural selection. So that's a theoretical explanation, a systematic explanation of what we also say is a fact about evolution. In other words, we've observed that biologists have accumulated lots and lots of evidence that evolution did in fact occur. So the word evolution is used to refer to both a fact and a theory scientifically. So people that say, if it's only a theory, why do you call it a fact, are thinking that when scientists say it's the theory of evolution, that scientists are saying, well, we're guessing that it might have occurred, when in fact the theory of evolution refers to an explanation, not to a guess. That's what it comes down to. And it's a very well-supported explanation. Typically, we don't call things theories in science unless they are well-supported by evidence, which doesn't mean they can't be overturned. Like Newton's theory of gravity was in some sense overturned when Einstein came along and showed that we can understand gravity as a curvature of space-time. Even there, though, Newton's theory of gravity still works very well where it applies. So, is that a good enough explanation for you? Yeah. Okay. So, any follow-up questions on that? I try to remember, is there a follow-up on that? Is there something that you're not clear on before we go on to the next question? Hearing none. Did you have a question?
Yeah, I don't really catch like what the black body is during class the other day. I just didn't really.
Okay, so what's a black body? Right. So a black body, if we want to write out the definition, a black body is a perfect, and I put it in quotes because we have to say what we mean by that, perfect emitter and absorber of radiation. And by radiation I mean light waves, I mean electromagnetic waves, the whole electromagnetic spectrum. In terms of absorbing, by perfect we mean it absorbs 100% of the light that falls upon it. It never met a photon it couldn't eat. Which means that in the real world, there's no such thing as a perfect black body. It's an idealization. But there are things that are very good idealizations of black bodies. It absorbs 100% of the light that falls upon it and emits light with a characteristic spectrum. That depends only on its temperature. In other words, it doesn't depend on what it is made of. And by characteristic spectrum, I mean those curves that we showed for the brightness of light of different wavelengths from bodies of different temperatures. So there's a specific mathematical function that we can write down whose plot is one of these curves. And if this were like physics 280 or physics 380 or something like that, we in physics classes for physics majors and astrophysics majors, we actually write down what this function is. We don't need to do that here. I just want you to know that the plot of brightness versus wavelength has a characteristic shape. Something that you can write down in mathematical formula. And it's called the Planck function. So the thing is that, for example, my shoe is black, which means it absorbs most of the light falling upon it. But is it absorbing 100% of the light falling upon it? No, because you can see some light coming off of this. Otherwise, you wouldn't be able to see my shoelaces, or the fact that this is a little bit different than this, the structure of it and all that. If it were a true black body, it would be like staring into a black hole, and nothing would be coming back at you from it. You'd be seeing no light from it at all, unless it was warm enough. If it was warm enough, then it would be glowing invisible light. My shoe is glowing all right, but it's glowing in the infrared, so our eyes don't see. So black body is kind of a misnomer. It's only actually going to look black to your eyes if it's not hot enough to emit visible light.
So,
Yes.
so it only emits visible light, like if it's like hot enough?
Yeah, it has to be hot enough in order for light to be coming out of visible wavelengths. Now, strictly speaking, in principle, a black body of any temperature could emit some visible light, but it becomes extremely low probability at low temperatures. What I mentioned in class the other day is take a typical human body, the amount of surface area and so forth. You get about one visible light photon out of it about every 50,000 years or so. So you are unlikely to ever emit a visible photon as long as you live. So how are we seeing one another? If we're not giving off light, how are we seeing one another? Because I'm seeing you guys with visible photons, you're seeing me with visible photons. So how's that happening if none of us are giving off any visible photons?
It's the light reflecting off.
It's reflected, yeah. It's other sources of light are having photons that reflect off of us. And so we're seeing each other by reflection, not by emission.
So what would the spectrum of black body look like then? What do you even have a spectrum?
No, these are black body spectra.
Okay.
Yeah, so this is, and if a light bulb filament is a decent approximation to a black body spectrum when you heat it up. So a hot light bulb filament very much looks like a black body would look like at the same temperature.
Okay. So it would just be like one of those like little curves kind of.
Yeah, it would be one of these curves, and these are for different temperatures. So basically, it looks like a glowing thing if it's hot enough.
So if it's like 15,000 Kelvin, is that kind of?
Yeah, the 15,000 Kelvin one is this one. So what's it look like to our eyes? Well, here's the visible part of the spectrum, right? So its peak is in the ultraviolet. It emits most strongly in the ultraviolet if it's 15,000 Kelvin. But it's still emitting in the visible, and notice that it's emitting more short wavelength light than it is long wavelength light. And that's why it will look bluish to our eyes. A star that hot looks bluish in color because it's emitting in the visible part of the spectrum more blue, green, violet light than it is red, orange, yellow light. So our eyes will perceive that blend as a bluish color, is what it comes down to.
So if a black body is like 15,000 Kelvin, would it emit that bluish light?
Yep, yeah, if you could, now a light bulb filament heated to 15,000 Kelvin would turn into vapor, so you can't do it. But stars can get to that temperature, and they're vapors anyway. So, yes, a star's spectrum is very similar to a black body.
Okay.
And so a black body would look very much like a star does. A true black body heated to the temperature of a star would look pretty much just like the star does. The difference is would be that it wouldn't have any absorption lines in its spectrum. It would just be a pure rainbow with no colors missing. Unlike a real star, which has absorption lines in its spectrum. That's what's making it mostly not quite a black body. A black body doesn't have any dips in brightness anywhere like that. Sharp dips.
So would a black body have like an emission line spectrum or?
Nope, no. It's not a black body unless it has a nice smooth curve of brightness versus wavelength like that. So any black body that's hot enough to emit visible light, if you used a prism to spread it out, it would just look like a rainbow.
So they would, so they would only have.
Yeah, there's continuous spectrum, a rainbow with no colors missing. Yeah, if it doesn't look like that, it ain't a black body. Strictly speaking, a star is almost a black body, but we know it isn't because it's got all those absorption lines. So the rainbow part looks a lot like a black body spectrum, but the absorption lines are saying, well, it's not actually a black body.
So this is getting pretty theoretical.
Yes.
So the reason why it has that spectrum is because it has the cooler gas on the outside of the star.
Yes. So why does a star like the sun, or pretty much any star for that matter, why does it have an absorption line spectrum? So let's go back to the slide which talks about how you make the different kinds of spectra. Right? Remember that if you have a source if you have a hot light source, it's dense, it's a solid or a liquid or it's a dense gas, you get a rainbow spectrum, no breaks in it. If you have a hot, low-density cloud of gas, you get an emission line spectrum. So when I had the hydrogen lamp and I turned it on, heated up to a very high temperature, it was emitting an emission line spectrum. If you take that same cloud of gas and put it in front of a hot light source, you'll see a rainbow of colors coming from the hot light source, but atoms in the cloud are absorbing some of the light before it reaches the prism here, and so those colors are missing. So in the sun, what is playing the role of the cool cloud of gas and the hot light source is, the cool cloud of gas is the cooler gas in the sun's outer surface layers, and the source of the rainbow is the hotter, denser gas lower down in the sun. So a cool, lower density cloud, the cool, lower density, cooler, it's really still blazingly hot by human standards, but the cooler, lower density outer layers of the sun absorb light coming up from hotter, higher density layers of the sun. And the colors that get removed produce the absorption lines that we see in the suns or any other star spectrum for that matter.
So if you just had like this just before the sun, it would be like a continuous spectrum?
Yeah, if the sun were all the same temperature, if the sun was all at the same temperature, then it would be a source of continuous spectrum. But the fact that the sun gets hotter as you go inwards gives it absorption lines, because that means there's a cooler layer on top that is absorbing wavelengths coming up from the hotter layers below. Yep. Any questions about that? Any of that stuff? Yes?
So the emission line, if it's like truly a black body, it's going to be completely dark. Yet the stars, it appeared to be a dark body because you could see rainbow colors.
So, okay, so let's, there's a couple of things here. So one is, you have to be careful with the name black body because it doesn't imply that they always look black. I actually don't like the name black body because it sounds like there are things that look black, but they don't necessarily. A black body only would look black to human eyes if it weren't hot enough to give off visible light. If the temperature reaches a couple of thousand Kelvin or higher, it's hot enough that it starts to glow. So only a cold black body would actually look black to our eyes. A warm black body glows to our eyes. We would see it glowing. So stars are hot enough that they definitely glow. That's why they glow, is because they're hot. And if a star was a ball of gas all at the same temperature, then it would count as a hot, dense light source, and it would produce a continuous spectrum. But stars are not all at the, a given star is not a ball of gas that's all at the same temperature. It gets hotter as you go inwards. And so that means there's cooler gas on top of hotter gas below. The hotter gas below kind of acts like a light bulb, producing a really bright light bulb, producing a continuous rainbow spectrum. The cooler gas in the star's outer layers, atoms in that gas, absorb some of the light because they have atoms that have electrons that can jump up energy levels by absorbing photons of just the right wavelengths. So the cooler layer of gas in the star's outer surface area absorbs select wavelengths from the rainbow of light coming from below, and you get dark lines which represent the missing light that those atoms in the star's outer layers are absorbing that are coming up from below. Any other questions? Okay, next question then. Or a series of questions. Yes.
So like, just, I don't know, I'm asking, so like, for light is both, it says both an energy, light is both
Light
energy.
is both, what we say is it's waves and particles.
Okay.
Yeah, it has both wave nature and particle nature. So the joking answer, for a long time, scientists debated, is light a wave or is light a particle? They figured it's one or the other. It can't be both. How can it be both wave and particle? It's either waves or particles. Problem is, some experiments suggest that light is made of waves, and they seem to conclusively show that light is made of waves. But there are other experiments that seem to conclusively show that light is made of particles. So the actual answer, strangely enough, kind of the joking way to put it, is light a wave or a particle? Yes. In other words, it has characteristics of both. Sometimes it acts more like waves, sometimes it acts more like particles. Strangely enough, light is not alone in that. Electrons, sometimes they behave more like waves, sometimes they behave more like particles. The entire material world, it's all an illusion that there are particles, that there are actually literal like little hard balls or whatever that we might imagine atoms or whatever to be. In fact, all of matter has both wave and particle characteristics, depending on the conditions under which you observe it.
Are you going to give us all the equations for the exam?
Yep, I will give you any equations that you need to use to do any calculations with. Yeah. Your job is to know what to do with them, basically. And again, you won't need a calculator, you really won't. Which is not to say there's no quantitative questions, but the numbers will be nice and round so that you don't need a calculator. If you think you need a calculator, you're doing it wrong. There's something wrong with how you're approaching it. Yes?
So, for the hallmarks of science, I know that there's the three big ones, and then scientists want to seek the simplest possible explanation, which is Occam's razor.
Yeah, Occam's razor is the idea of seeking the simplest possible explanation that accounts for all the facts.
Is there an explanation other than they just want to find the simplest way to do it?
Yeah, so, it's like, why does Occam's razor work? That's actually kind of a profound philosophical question. But from a practical standpoint, it really does come down to, first of all, why would you use a really complex explanation when a simple one works just fine? And in practice, we get away with it. In other words, for whatever reason, it seems to be a good guide to how the universe works. Seeking the simplest possible explanation has not generally led us astray. Which is not to say there couldn't be a situation where some really complex explanation was the right one, but in general, we just, for whatever reason, find if we can come up with a simple explanation, it tends to hold good when we keep pressing and trying to try it under different circumstances, kind of generic. But certainly from a practical standpoint, right, why speculate that there are gnomes in the garden that got rid of the weeds when a better explanation might be that your husband went and weeded the garden, that sort of thing. So. Chirp is the cricket's chirping. Yes?
Can you go over why Newton's law of gravity is an inverse law?
So the question is, can I go over why Newton's law of gravity is an inverse square law? And I think the way I'm going to interpret your question is to say, what do you mean by inverse square law? Because why? Nobody knows that. In physics, we can figure out what the laws of physics are. Why they are the way they are, that's a much tougher question. So what I can tell you is what an inverse square law is, and I can't tell you, because nature thinks it's a good idea, or if you're religious because God likes inverse square laws or whatever. We can't say why the laws of nature are what they are generally. We just say what they are and what their consequences are. So The force of gravity is gravitation constant g times the mass of the first object times the mass of the second object divided by the square of the distance between them. To say that it is an inverse square law is to say that you divide by the distance squared between them. That's all there is to it. Inverse square law, inverse means it's in the denominator, square means it's squared. So inverse square law means you divide by the distance squared to figure out its contribution to the strength of gravity. So if the objects get further apart, that's down there in the denominator. So that's saying that if I divide by a bigger number, the result is smaller. So if the objects get further apart, then the force of gravity that they're exerting on each other gets weaker. And you have to square whatever you did to the distance. So if you make the distance 2 times bigger, the force of gravity is only 1/4, 1 over 2 squared times as big as it was before.
So can you like please explain why or how Wien's law and the Stefan-Boltzmann law relate to the color and luminosity of stars?
Yep, so how do Wien's law relate to colors and luminosities of stars? So the Stefan-Boltzmann law is the one that says that the total amount of energy coming out of each square meter every second is this universal constant of nature times the temperature to the 4th power. So this right here is saying the higher the temperature is, the more light is coming out of each part of the surface. So, and we're later on, we're going to do this in quite a lot of detail. If I have 2 stars that were the same radius, the same size, and one of the stars was hotter than the other one, what would that imply about their luminosities, about the total amount of light they're giving off? If I have 2 stars, they're both the same size, but one is hotter, which one will be brighter? Which one will be giving off more light? The hotter one or the cooler one? Definitely the hotter one. In detail, it's because every square meter of the hotter star's surface is giving off more light. That's what the Stefan-Boltzmann law is saying. It becomes more complicated if you have a really big cool star and a tiny hot star. Well, then you've got competing effects. Then you've got, well, the big star has a lot of square meters to radiate from, but each one isn't radiating that much. And so then you'd have to run the numbers, and that's something that we'll be doing a lecture tutorial about. But if the 2 stars are the same size, the hotter one will definitely give off more light because every square meter of its surface is giving off more light. And then the Wien's law is the one that says, well, this is in terms of temperature given by the peak wavelength, but I can also, as I mentioned in class, I can also write this, that the peak wavelength is that number up on the top, 2.9 times 10 to the 6th nanometer Kelvin divided by the temperature. This says as the temperature goes up, what happens to the peak wavelength?
Goes down.
Goes down. And so that shows up in our plots here, where the higher the temperature is, 2 things happen. One of them is the peak wavelength. The value of lambda corresponding to the top of the curve, the peak of the curve, gets shorter and shorter as the temperature goes up. So the cool 3000 Kelvin star, its peak wavelength is in the infrared. The hot 15,000 Kelvin star, its peak wavelength is in the ultraviolet. Shorter wavelength than the peak wavelength of the infrared star. And for the sun, around 5800 Kelvin, the peak wavelength is yellow-green. So the idea is that this is explaining why there's a difference in the colors of stars based on their temperature, because the 3000 Kelvin star, even though its peak is in the infrared, there is light in the visible part of the spectrum, but it's mostly red, orange, yellow light and not so much green, blue, violet light, so that blend of colors looks kind of reddish orange to a human eye. For the sun, you get a more nearly even, it peaks at yellow-green, but it's a fairly even blend of all the colors, and our eyes call that white, or maybe a little yellowish white. The blue star, again, as we were mentioning before, emits across the visible spectrum, but it gives more green, blue, violet light than red, orange, yellow light, so that blend looks bluish to our eyes. So we can understand the changing color as the temperature changes in terms of Beam's law because of that idea. And we can understand the Stefan-Boltzmann law actually turns out to be the total area under the curves, but also every wavelength gets brighter as the star's temperature increases. And Stefan-Boltzmann law is describing the idea that all else being equal, a hotter star will be a brighter star. If the size is the same, so that there isn't that extra complication, if two stars that are the same size, the hotter one will be giving off more light, says Stefan Boltzmann. And says common sense too, right? I mean, it's intuitive that hotter is brighter, probably. But Stefan Boltzmann makes that precise, tells you how much brighter for a given amount of hotter, so to speak. So I just want to double check. Is the light on the back of the camera still blinking red? Okay. If it ever stops, please let me know, because that would mean it stopped recording. But I can't see it from where I am. So. Hello, audience at home. Yes?
Could you go over Occam's razor again?
Sure. Occam's razor is the idea. It's deja vu, but it's quick. So Occam's razor is the idea that if I have two explanations and they both do an equally good job of explaining the facts, then just from a practical standpoint, pick the easier one, pick the simpler one. And that sounds like common sense, and it is, but in fact, it's a guiding principle for scientists. In other words, generically, if we have some really complicated theory that explains a bunch of observations versus some much simpler theory that will do the same job, pick the simpler one. And for some reason, that seems to work. In other words, even when we then try it out with other situations, often we find that the simpler explanation ends up working. But it can happen that, so one of the things that Einstein is said to have said, and I'm pretty sure he actually did his words to this effect, he would have probably said it in German, but you want to choose something like this. Choose the simplest explanation possible, but no simpler, right? In other words, it's got to be the simplest explanation possible. Occam's razor doesn't say simpler is always better, because if you make your explanation too simple, there might be stuff that it can't account for. So it has to account for everything. It has to be the simplest explanation that will account for everything. Einstein's theory of general relativity is mathematically much more complex than Newton's theory of gravity. So if all we were trying to do was to fly spacecraft in our solar system, there would be no good reason to use Einstein's theory of general relativity, and if all the observations we had corresponded to the regime where we can use Newton's theory of gravity, even though Einstein's theory gives essentially the same results, you wouldn't want to use Einstein's theory. However, there are circumstances where Einstein's theory gives the right results and Newton's theory gives the wrong results, which is why we still pick Einstein's theory, even though it's much more complex than Newton's theory, because Einstein's theory can explain things that Newton's theory cannot. And it can explain all the things that Newton's theory can as well. So it's a more general theory than Newton's is, even though it's more complicated. So it's not choose the simplest explanation, it's choose the simplest explanation that will do the job.
So it's entirely contingent on if they're still both essentially equal and equally valid.
Right,
And
they
so-
both, yeah. If the more complicated theory does a better job, well, you pick the more complicated theory. But if they both do an equally good job, pick the simpler theory.
Okay.
Yes.
So, in our tutorials, with the Doppler shift,
Yeah.
there's a question that asks, it shows us 4 different spectral lines, and then it wants to know, would this star be moving toward or away from Newton's theory? Like, how exactly does knowing the wavelengths or the...
So I better see exactly what it
Yes.
says here. So which one is this? It's, it would be on page 77 of your lecture tutorials, part 3, size of shift and speed. So it says, consider the four spectra to the right. The spectrum labeled F is an absorption line spectrum from a star that is at rest. Again, note that short wavelength blue light is shown on the left, long wavelength red light is shown on the right. And then it asks some question, I presume, right? And then it says, like, which one is from the star that is moving the fastest, right? That sort of thing. Okay. So in that example, it is a given that one of those is for a star that's at rest. So those are the same wavelengths you get in the laboratory, the undoppler shifted wavelengths, right? So I think the way to explain this is there's conveniently enough a mastering astronomy problem, which is very similar, which involves exactly the same kind of reasoning. And now I have to see if the name of it will tell me which one it is. I think it's like a ranking task, Doppler shift of light. Yeah. Okay. So it's the one that's ranking task, Doppler shift of light in the chapter 5 one. And let me expand this thing out. So here is, which one of these do I want to talk about? Yeah, so here is a bunch of spectra, okay, pairs of spectra, and on the top is the lab spectrum, which in that lecture tutorial would be the same as the one for star F that is at rest. In other words, if a star is at rest, the wavelengths of its spectral lines are exactly what they would be in the laboratory, because there's no Doppler shift. So you can think of on the top here, that's always star F in that lecture tutorial. And then below it is the spectral lines of some star. And you're supposed to rank from largest blue shift to largest red shift. And the way you're always going to approach something like this is, okay, first of all, you just got to burn it into your brain, or think of the diagram in the book of a train coming towards you versus away from you. So if the star is moving towards you, is that red shift or blue shift? Blue, right? So towards is blue shift. The waves get piled up closer together, the wavelengths get shorter for something that's moving towards you. And if it's moving away from you, it's red shift. So that's part of it, is I know that if the wavelengths are blue shifted, now, and does that mean shorter or longer? If it's blue shifted, does the wavelength get shorter or longer? Shorter, right? So if the wavelengths get shorter, that's a blue shift, it's moving towards me. If the wavelengths get longer, that's a red shift, it's moving away from me. Right? So that's something you want to keep in mind with anything like this. Wavelengths longer says red shift, says moving away, and vice versa. Wavelengths shorter says blue shift, says moving towards. And it doesn't matter if you think of it as you're moving towards it or it's moving towards you. Motion is relative. So if two things are moving towards each other, they'll see a blue shift of one another's spectral lines. If two things are moving away from each other, they'll see a red shift. And furthermore, the bigger the shift, the faster the speed towards or away. So it's actually very systematic. The more shift there is, the faster it's moving towards you or away from you, just like you might expect. So with these guys here, if I want to, if we just go through them, this guy right here, okay? So I don't know how well you can see from back there, but in this one, all the spectral lines are perfectly lined up between the star and the lab spectrum. So how much Doppler shift is there? Zero. So is this star moving towards us or away from us, or neither? Neither. It's either at rest or it's moving side to side. So that's going to be the one that's somewhere in the middle because it has neither a redshift nor a blue shift, so that's going to be the middle one. This one right here, okay, so the lab spectral lines versus the star spectral lines, I don't know how well you can see it, but the star spectral lines are to the right of the lab spectral lines. So is that redshift or blue shift?
Redshift.
That's redshift, so is that going to be moving towards us or away from us?
Away from us.
Away, and it's going to be somewhere on the redshift side of the picture, right, when you're ranking it. This one in the middle here, the spectral lines moved to the left. Is that redshift or blue shift? Blue shift, so it must be moving towards us, and it's going to be over here somewhere. Note carefully, here's the red spectral line that got blue shifted. It's still red. It's a different shade of red, but it's still red. So redshift, blue shift just means shorter, longer. It doesn't say anything about the final color per se. And we can go through the whole list, and what you do is you put the one whose spectral lines shifted farthest to the left as largest blue shift, and the one whose spectral lines shifted farthest to the right as the largest red shift. So which way it shifts tells you blue shift or red shift. How much it shifts is larger red shift, larger blue shift, larger speed. So it could also have said fastest motion towards us, fastest motion away from us. It would be the same ranking because how much shift tells you, how much of a shift there is tells you how fast it's moving, and whether it got shorter or longer tells you whether it's towards or away. So this part of that one is more quantitative, where it says that the laboratory wavelength is 656 nanometers, and then they give a bunch of wavelengths. So if the laboratory wavelength is 656, and in the star it's 646, did it get longer or shorter? Shorter, right? It got shorter. The shift is it got shorter. The change is it got shorter. So is that a red shift or a blue shift?
Blue shift.
Blue shift. Shorter means blue shift. So is it moving towards us or away from us?
Towards us.
Towards us. That's the logic. You say, first of all, did the wavelength get longer or shorter? If it's longer, that's a red shift. It's moving away from us. If it's shorter, that's a blue shift. It's moving towards us. It's that way every time. That is the logic. Does distance to the star have anything to do with it? Nope, it doesn't. Does the color of the star have anything to do with it? Also, no. All that matters is how much did the wavelengths of the spectral lines change. Doesn't matter what color the star is, how far away from it is. All you care about is how much did the wavelengths change, and all that tells you is how fast is the star moving towards us or away from us.
What's the color and energy levels? Blue
Yeah,
is
so with color and energy levels, so remember that if I write it as a formula, and again, I'll give you formulas, but the energy of a photon is that number hc times the wavelength of the photon, which works out to be 1240 electron volt nanometers divided by the wavelength of the photon. So this formula is telling you, and you should just memorize this too, just realize it, that the shorter the wavelength is, the higher the energy is. Shorter wavelengths mean higher energies. And if you think of it in terms of, if the wavelength is shorter, more waves are passing by you every second, it's kind of intuitive that ought to mean higher energy. It's waving faster, so to speak, and so it's kind of plausible that that means higher energy. Longer wavelengths, it's waving slower, and so it's slower energy. Yes?
It's about momentum. For one of the mastering astronomy, it's a sorting thing, and two of them, in particular, that confuse me. One is a planet is orbiting the sun in a circular orbit, and a car is holding a steady speed around a curve, and those are considered changes in momentum.
Yes.
But how? Because momentum is only mass times velocity, and so if there.
Yeah, see, there's the thing, right? So I see where you're going, right? I see what you're saying. Momentum is mass times velocity, but velocity is a vector. In other words, momentum isn't mass times speed. Remember that in physics, even though in everyday language we use velocity and speed as synonyms for one another, in physics, velocity is the combination of speed and direction. So, and the shorthand way to say that is velocity is a vector. And since momentum is mass times velocity, that means momentum is a vector too. Momentum has not only size, how big it is, but also direction that it's pointing. So if you're going around a curve, if you're going around a circle, even if I'm going at a constant speed, the direction I'm heading in keeps changing. Right here I'm moving this way, right here I'm moving this way, right here I'm moving this way. So it's acceleration because the direction is changing. Any change in speed, which is how fast you're going, and or direction is acceleration and requires a force to make it happen. It's a change in momentum, and forces change momentum. Yes?
When I studied astronomy, we were asked to rank the electromagnetic spectrum, like in terms of speed. They're all the same.
They're
right?
all the same. That was kind of a trick question to be sure that you understood that in a vacuum, and pretty close to in air too, because air is very low density compared to like solids and stuff. So in space, all electromagnetic radiation travels the same speed no matter what its wavelength is. So yeah, if you're asked to rank the following forms of magnetic radiation according to the speed that they travel through space, well, they all travel at that same speed of light, c equals 300,000 kilometers per second. So yeah, all just dead. I'll be taking a nap here. Maybe you have a question.
I'll be going home.
You're going home.
Okay, I got all
All
right,
right.
so.
Okay.
Good luck tomorrow, today.
Well, we need to know where certain elements are, like spectral lines or colors.
No, I want you to know that different elements have different spectral lines, but I certainly don't expect you to, like, I would show you a spectrum and you say, oh, that's praseodymium, or something like that. Just know that they have different spectral lines because they have different energy levels that their electrons are allowed to jump back and forth into.
Thank you.
Good luck. Yes?
Shorter wavelength on electromagnetic means higher frequency.
Shorter wavelength means higher frequency, for any wave for that matter. Shorter wavelength means higher frequency, and the reason is that the frequency is how many ripples pass by you every second. And since since all the light waves are traveling at the same speed, if the ripples are much closer together, more of them are going to fly past me every second. And so it's automatically true that shorter wavelength means higher frequency, just because if they're closer together, more will pass you every second. Just like if you had a parade of people, the closer the people are together, if they're walking past you, the more people will pass by you every second.
So when so in the case of like the hydrogen or neon in a tube, and so light is only emitted when electrons have been jumping down.
Yeah,
And so
that's
you-
what, yeah.
And then when you charge them up, they jump up. So,
Yeah, so the way that's working is that if an atom absorbs a photon, it jumps up.
Yeah.
In that tube, what's happening is collisions can also make electrons jump up in energy, and that's what's happening in the tube. Things are bumping together, and collisions are bumping electrons into higher energy levels. And then when they fall back down, they give off photons. They give off the light that we're seeing.
So when there's a continuous energy source, and wouldn't that make all the atoms jump up to the highest levels because it's continuous?
No, it's more complicated than that, because when you have a dense material as opposed to a low density gas, there becomes more ways for light to be emitted. So for example, if two atoms pass by one another, they'll feel one another's electric fields. That will cause them to accelerate because they feel a force. It turns out that charges that accelerate give off light. And so a solid or a liquid or a dense gas where the atoms are interacting, jiggling and so forth, it has more ways to give off light than just electrons jumping up and down between energy levels in individual atoms. And that's why you get a continuous spectrum as opposed to an emission line spectrum when you have something dense.
And what about the visualization when it's an atom and you have to draw a photon coming in, which hits the electron, so which would bump it up, and then vice versa if it jumps up. In terms of drawing it, the photon going out can go out in any direction, doesn't
It
it?
can go out in any direction, that's right. It can go out in absolutely any direction. And in fact, that's key to why we get the absorption lines, is that if I have a beam of light coming in my direction and atoms absorb some of those photons, well, those atoms will drop back down and emit photons again, but they'll spit them out in random directions that are not part of the original beam, which is why they're missing from the original beam, even though they're there, they're just not moving in our direction anymore.
Okay, that explains why actually.
Yeah.
Yeah. There was a question on mastering astronomy I didn't want to do last night. question is being, what is the wavelength of maximum intensity for this light bulb, and the temperature of the light bulb or the coil is 3,000 Kelvin. And I don't know how I got this, but how do you calculate that? And what's
Yeah,
the-
that's Wien's law in
Wien's law?
action. Yeah, for the maximum intensity, Wien's law says what we call lambda peak, which is also often called lambda max, the wavelength where the spectrum is brightest. In other words, like for this curve right here, this wavelength right here is lambda peak for this curve. And Wien's law says, if I flip this around and put lambda peak here and t there, lambda peak is this number, 2.910 to the 6th nanometer Kelvin, over the temperature. So if I know the temperature, I take 2.9 million, divide by the temperature, and that's the wavelength for peak in nanometers. So you literally plug the value of the light bulb's temperature into the denominator here, and the number that comes out is lambda peak.
Okay. Well, we need to know those top numbers.
The
Like
numbers?
The constants, like the 2.9.
No, I will give you anything you need like that.
Okay.
But the thing is, as I said, I'm going to keep the numbers round. So in other words, if you think you need a calculator, you're doing something wrong. I'm going to keep the numbers nice and round. So for example, like we were talking about in class last time, with this, what's also true is that the ratio of the peak wavelengths is the reciprocal of the ratio of the temperatures. So in other words, if I have two black bodies, then the peak wavelength for the second one divided by the peak wavelength for the first one is T1 over T2. So if I made the temperature 10 times harder, the peak wavelength would only be 10 times higher. The peak wavelength at the new temperature would only be 1/10 as big as before, for example. It's a reciprocal relation because the T is in the denominator in the expression for the lambda. So it makes it flipped over when you take the ratio. And then notice you don't need anything about what this number is. The 2.9 times 10 to the 6 doesn't even show up.
Because they cancel out.
Because it canceled out, yeah. That's a good thing about ratios, is things like those constants just cancel out. You don't even need to know what they are.
Oh, and a similar one. It's using the other law.
The Stefan Boltzmann one, yeah.
Maybe not. It's the supposed surface of the sun were 40,000 versus 6,000. And so it's the how much more thermal radiation the sun.
Right, yeah, so that's another one where you're looking for a ratio.
Yeah.
And because the flux is that number sigma times the temperature of the fourth power, there you would say, okay, if there's two temperatures, T2 and T1, or T2 over, for the flux from temperature T2, something at temperature T2, over the flux from something at temperature T1, you'd have sigma T2 to the fourth over sigma T1 to the fourth. Again, the sigmas cancel, so you get T2 to the fourth over T1 to the fourth, but there's another rule of algebra that says that the ratio of the powers is the power of the ratio, so to speak. So in other words, the flux ratio is the fourth power of the temperature ratio. Put another way, if I, for example, made the temperature 4 times bigger, then the flux would become 4 to the fourth power, 256 times bigger as a result. And so again, if you're just asked for a flux ratio, you don't need to know what sigma is. I don't even have to tell you what it is, because it's just going to cancel out. And in the mastering astronomy, you know, you get like 40,000 and 6,000. So yeah, you need a calculator to figure out what 40,000 over 6,000 to the fourth power is.
Right.
I would give you examples where the temperature got 3 times bigger. What happens? You know, that sort of thing. If you could recognize, well, you could, in other words, I give you a nice round number for how many times the temperature increased. Something that you wouldn't need a calculator to raise to the fourth power.
You said for the principle of the law, how it works.
Mm-hmm.
Okay.
So for the multiple choice, will it be similar to the setup of like the concept quizzes through astronomy?
Yeah, it'll be quite similar to the concept quizzes, or for that matter, the quizzes I've given in class. Yeah, same kind of questions, just multiple choice, and you know, pick whichever one is right, and write it in the blank or whatever. Yeah. Mhm. Question, okay, yes.
Can you just go over the uniform circular motion that you have on the exam review talking about a ball being spun?
Right, so uniform circular motion, how it relates to gravity. Oh, that's interesting. Apparently there was a meteor shower on Mars that was the most intense ever recorded on it. But anyway, because space.com sent me announcements. So that would be the chapter 3 thing here. And did I go wrong with that? Oh, no. No? Oh, okay. Well, anyway, there's a thing in the book that talks about it. What was this? Oh, making sense of the universe. There, that's what it's yeah, okay. So it goes with this slide from Making Sense, Chapter 4, Making Sense of the Universe chapter. So, uniform circular motion involves acceleration because you're not having it move in a straight line, so it's bending away from straight line motion. So that means it requires a force. Okay, we can actually figure out which way that force has to be by imagining the following. suppose you got, like I did growing up, a little sister. I had 3 little sisters actually, okay? You pick up little sister, and you start swinging little sister around like this. So, if I let go of little sister, what's she gonna do?
Be thrown.
Yeah, she's gonna fly off in a straight line. Well, she'll also be falling down too, but ignoring the falling down part, the horizontal motion is she would just be moving off in a straight line because there's no force on her. So I'm exerting a force on her to keep her moving in a circle. If you were doing that, if I'm doing that, do you have to push out on little sister or pull in on little sister to keep her moving in that circle? Do you have a sense for that? If you're holding on to something and spinning around in circles, you're going to have to pull inwards or push outwards. What's that? Yeah, inwards. You have to pull inwards. Yeah, you have to pull inwards in order to keep something moving in a circle around you. That must mean that the force required to produce uniform circular motion is inwards. The ball on the string idea is, here's a ball on a string. In that case, instead of your arms directly holding it in motion in a circle, it's the string. There's tension in the string that pulls inwards on the ball and gives it its acceleration towards the center of the circle that is needed in order to keep it moving in a circle around you. So now consider the moon going around the Earth. It's not a perfect circle, but it's pretty close. There must be an inwards force on the moon holding it in a circle, holding its motion in a circle. It's not created by a giant rope that is tied between the Earth and the moon. Something else is providing the inwards towards the Earth force on the moon that holds its motion in a circle. What is that something else? What is providing the force on the moon that holds its motion in a circle? Say it loud, say it proud.
Gravity!
Gravity, yes. Earth's gravity is the string, so to speak. Earth's gravity is acting like the string that pulls inwards on the moon so that it will move in a circular motion. Really, it's an ellipse, but whatever, it's almost a circle, as opposed to just flying off in a straight line out into space.
What is the relation between Celsius and Kelvin?
They're shifted. A degree Celsius is the same size as a Kelvin, but they're shifted by 273.15 degrees. In other words, on the Kelvin scale, absolute zero is 0 Kelvin. But on the Celsius scale, absolute zero, where you can't remove any more thermal energy, is minus 273.15 Celsius. Other than that, so in other words, there's just a constant shift of about 273 degrees between Kelvin and Celsius. When you get to something as hot as the sun, it stops mattering much because it's thousands of Kelvin, and so a few hundred Kelvin isn't making that big a difference, especially if you get like to the core of the sun where it's 15 billion Kelvin. But on Earth, for example, then you would definitely see a big difference between the numbers. Like room temperature is like, about 270 Kelvin or something like that, which sounds very warm, but it's just because that's above absolute zero. Or 290 Kelvin, I mean. So that's how far it is above absolute zero. Kelvin scale, your body temperature is around 300 Kelvin. Yes?
I'm sorry for explaining this. It's just problem 5.51. Could this be a simpler question that we may come across?
5.51. Let me pull
Yeah.
that up. So, Right, so that's the one. What is the wavelength of an X-ray photon with a certain energy? 9,000 electron volts per me, but every student gets a different number because that way you can't, we don't want, one student does the calculation and then tells everybody the number and they all put it down, so it randomizes the numbers. So this is an application of this idea that the wavelength is, for a photon, is hc divided by the energy, which is 1240 electron volt nanometers divided by the energy. So again, this is one where here it's just giving you some random energy, and so you need a calculator. But the way I could make it gentler to where you wouldn't need a calculator is if I made the energy exactly half of 1240, for example, like I did in class. So if I made the energy, actually that would be the wavelength in that case. But if I made the energy a nice, sorry, I'm doing this backwards, aren't I? Yeah, I wanted a different version. That's fine. So this is true, but no, this is the version I want. Okay, never mind. If I had the energy being, say, 2 electron volts, then you can do, well, 1240 over 2 is 620, that sort of thing. Truth be told, though, 1240, yeah, not too hard to divide, things by that, by hand or whatever, but that's a little bit, not everybody is equally good at saying 1240 over 2 is 620. And when I say shouldn't need a calculator, I mean really what should be quite simple calculations, where, as I keep saying, quantitative reasoning isn't always putting difficult numbers into a calculator and getting the answer out. Just as important is being able to do quick and dirty calculations or simple calculations to see what happens when things change. In many ways, that's more important in many contexts, understanding how things will change, how one thing will change when you change another thing. That's what gives you actual insight into what's going on, as opposed to just putting numbers into a calculator and not really thinking about what it means. See you later, buddy. Yes?
Final question. When a bug and a truck smash
Mhm.
together,
Yeah.
is it mass that makes the
It's the difference in masses,
Okay.
right? Because how do the forces compare?
the same bug?
They're the same, right? They're the same. But the truck is so much more massive than the bug that force hardly affects the truck, whereas it gives the bug a really, really deadly acceleration. in particular, different parts of the bug, the details of the collision or the different parts of the bug are actually experiencing different accelerations, which is why it goes splat, essentially. Because there's a certain kind of overall force on the bug, but during the collision, the force on the part that's hitting the truck is higher than the force on other parts of the bug, so as a result of that.
What does it mean to ionize an atom?
It means to remove electrons from it.
Okay.
Ionization means to take electrons off of the atom, to strip off electrons by giving them enough energy that they break their electrical bond with the rest of the atom.
And how does that happen?
A violent collision of the atom with another particle can do it. So can a photon, which has enough energy. So an ultraviolet photon can ionize an atom, or a molecule for that matter.
And that's why it's bad for you.
That's one of the reasons, yeah. And beyond that, they can also just break chemical bonds in molecules. And so you can create what are called free radicals, little molecular fragments that move very fast and then they can damage other molecules. Or they can just be very chemically reactive and damage other molecules because of that.
So ultraviolets are obviously fairly strong. And so everything that's past ultraviolet is even stronger. That's why.
Yeah, so that's why you don't want to expose
even
yourself
worse.
to X-rays unnecessarily.
Oh,
Yeah,
that's cool.
because it's so-called ionizing radiation.
Yeah. No kidding.
Yep. That's why, sometimes it's reported or claimed that cell phones are giving people brain cancer, for example. But there's no really good evidence for that. There's some evidence, and it can't be entirely excluded, but it's hard to understand why it would, because cell phones are giving off low energy photons. Those are very low energy photons. As a result, they can't ionize anything. They don't have enough energy to have a significant effect on any chemicals within your brain or anywhere else in your body. So it's hard to find a mechanism that will explain why they might cause problems. They could cause a little bit of heating, but it's hard to believe that that tiny amount of heating would be a problem.
Thank you.
You're welcome. See you later.
Yeah, I wish I had more, but I really don't.
That's fine.
Yeah, it's kind
I
of.
need to eat dinner anyway, so,
Right.
yeah, all right,
Thank you.
you're welcome.